Okay, so this is, I believe it's this, it's either day 1 or day 2 of composing functions. But what they're asking you on this is, remember that whatever is inside your parentheses becomes the input into the function. So if they're asking you what is the output when your input is w, you would just take w and plug it in wherever you see an x. So this would become w squared plus 2w minus 1. And that's all the farther you can take that one. These are not like terms because this is w squared and this is just w. Same thing for this one. So if you take a minus 1, this is your input. So wherever you see an x in this equation up here, it gets replaced by this a minus 1. So the a minus 1 needs to stay in parentheses. So a minus 1 squared plus 2 times a minus 1 minus 1. And then we have to expand these pieces right here and then combine all of our like terms. So if we do a minus 1 squared, remember that that is the same thing as a minus 1 times a minus 1. And we have to distribute both the a and the negative 1. So if we take a times a, we get a squared. A times negative 1 is negative 1a. And now we distribute the negative 1, so negative 1 times a is negative 1a, and negative 1 times negative 1 is positive 1. So when we combine our like terms together, we get a squared minus 2a plus 1. So this part right here replaces this part right here, this whole a minus 1 squared. So a squared minus 2a plus 1. And then with this part, we just distribute the 2. So plus 2a minus 2, and then the minus 1 just drops down. So now with this part, all we have to do is combine all of our like terms. So the a squared doesn't have anything to combine with, so it just stays a squared. The minus 2a here and the plus 2a here are going to cancel each other out. The positive 1 here and the negative 1 here are going to cancel each other out. So then you just bring down the minus 2. So the output of g, when your input is a minus 1, is a squared minus 2. Okay, and then the last one you have a cubed. So again, this is our input. It's going to go in wherever we see an x in this function up here. So we would have a cubed, and this is squared because we have x squared here. So we need to keep the squared here. Plus 2 times a cubed minus 1. So when we have a cubed squared, what that's saying is a cubed times a cubed. And when we have the same base, we can add the exponents together. So this is a to the 6th power. So really this is kind of like the distributive property for exponents. So you have a to the 6th power plus 2 times a cubed is just 2a cubed, and the minus 1 just drops down. So this would be the output when you plug a cubed into g. Okay, so today, compose functions and decide whether a function has an inverse. So this is just 2 different ways to show composition. So we can either say, you can kind of ignore this part right here. We'll come back and talk to this in a second. We have 2 ways that we can show composition. So we could say f of x, g of f of x, or we could say g of f of x. These 2 things are the same. They mean the same thing. They are interchangeable. There is no difference between these 2 pieces right here. Typically what we've done is we've shown this one. In some cases now you might start to see this little open circle in between. So if we look up here at this input, x goes into the g function, and whatever comes out here goes into the f function. So x is what you started with, g is the first function that it went into, and then it went into the f function. So this is kind of like the order of operations for your composition of functions, and this is what it looks like out here, okay? So remember, the one that's closest to the x is the one that's closest to the x in here. The one that's farthest away from x over here is the one that's farthest away from x over here. Okay, so this is basically just some notation for you to know. G of f represents a function, okay? So it is a separate function from g of x or from f of x. It takes those two functions and creates a third function, which is what they're talking about down here. The identity for addition. So you can think of this as what would you add to something else to get back the same number? So if I wanted to add something to 3 and get 3 back, what would I add? You would add 0. The identity for multiplication is what number do you multiply times anything to get the same number back? So if I wanted to multiply 3 by a number to get 3 as my answer, I would have to multiply by 1.
A various
Sorry. Okay, so the identity for composition is just whatever you put into the function, you get out the same input that you started with, okay? Kind of an odd concept to think about, but if you were to plug x into a function, if you get x back, then that's your identity, okay? So additive inverse you can think of as what would you have to add to A to get your identity, okay? So like if you had 3 plus what is equal to 0? You would have negative 3. 4 plus what is equal to 0? You would have negative 4. So if you have A plus something is equal to 0, all you're saying is that it's the opposite of A. And the same thing you could do for negatives. Negative 4 plus what is equal to 0? You would have positive 4, okay? So it would be the opposite of A. Multiplicative inverse, what would you have to multiply A by to get 1, okay? So if you think about 2 times what is equal to 1? 3 times what is equal to 1? For 2, if you take 2 times 1/2, you would get 1. For 3, you would take 3 times 1/3 to get 1. For 4, you would take, you would take 4 times what to get 1? 1/4. So if you had A times something to get 1, what would go here? It would be 1 over A, okay? And do composites have inverses? It's whatever function gives you back the original input that you started with. So if you had f of g of 2, and then you did g of f of 2, it would give you that same input back both times. Again, this is just some notation for you to get used to. Okay, what operations are commutative? Commutative means you can switch the order and still have them be the same thing. So if you do 3 times 4, it's the same thing as 4 times 3. If you do 3 plus 4, it's the same thing as 4 plus 3. Is composition commutative? Only in certain situations. Okay? This one down here, you don't need to worry about. It's basically just saying that your g of f, you plug A in, you get, okay, sorry. So all this is just saying is that if you input A into F, then whatever you get for that, you plug into G, you get another output altogether. So, and then also remember notation here. These two things mean exactly the same thing. They're interchangeable. All right. So for you to do, this is just kind of to get you thinking about what these things mean and to get used to the notation. So show that f of g of 5 is equal to 71. So you're starting with g of 5, so you're going to take 5 and plug it into the g function. So that would give you 5 plus 1, which is 6. And then you're going to take that output and you're going to plug it into the f function. So you would have f of 6, which is 2 times 6 squared. And remember, we do exponents before we do multiplication. So this would be 2 times 36 minus 1. 2 times 36 is 72. 72 minus 1 is 71. So that's all that's asking you to do is just verify. Find these 3 different compositions here. So g of f of 5. So one thing that you're going to see is when it talked about our compositions commutative. Okay, so here's f of g, and we're going to do g of f of 5. Are we going to get the same answer? So that's what it means for composition of functions to be commutative, is if you plug the number 5 into g and then that output into f, or whether you reverse the order, do you get the same answer? So if we do g of f of 5, so f of 5 would be, I'm just going to do this one down here. F of 5 would be 2 times 5 squared minus 1, which is 2 times 25 minus 1, which is 50 minus 1, which is 49. So then we take that output and we make it the input for the g function. So 49 plus 1 is equal to 50. So this answer right here is 50, okay? F of h of 5, so the first one we're going to start with, we're going to start by plugging 5 into the h function. So again, I'm going to do this one straight down here. So 4 times 5 cubed minus 3 times 5. 5 cubed is 125. And we're going to multiply that times 4 and then subtract 15. So 4 times 125 is 600. And then subtract 15, we get 585. And then we're going to take that output and we're going to put it into the f function. So f of 585. So we're going to take 2 times 585 squared minus 1. So 585 squared is 342,225. And then we're going to multiply that times 2 and then subtract 1. So if we multiply that times 2, we get 684,450. And if we subtract 1, we get 6,000, I'm just going to write this one up here, 684,449, okay? And then now we're going to reverse these two. So we're going to do h of f of 5. So first thing we're going to do is we're going to take 5 and plug it into the f function. So that out of there. So 2 times 5 squared minus 1, so 2 times 25 minus 1, 50 minus 1 is 49. So we're going to take this and plug it into the h function. So 4 times 49 cubed minus 3 times 49. So 49 cubed would be 49 times 49 times 49, which is 117,649. And then 49 times 3 is 147. So if we take 4 times this 117, 649, we get 470,000. And then we're going to subtract out the 147. And I may have done this wrong. 117, 649 times 4 equals 6. Oh. I think you should get the same thing on both of these. So I may have made a mistake somewhere. So this 475.96 minus 147, 470,449. So I'm about 300,000 or 200,000 off with that one. So let's see. Oops. Oh, this is 500 here. I'm sorry. So this should be 485. So this should be the correct answer, I'm sorry. So 485 235, 225 times 2 is equal to 470,450 minus 1, and this should be the same as this one. So in this case, these two are commutative, but it doesn't necessarily mean that all of them are going to be commutative. So 470,449 here, 470,449 here. Okay, and then the last one is saying find formulas for f of g and for g of f. So what that's asking you to do is, for f of g, they're asking you to use the g function as the input into f, and here using the f function and using it as the input for g. So for example, if we wanted to find the formula for f of g, you would take the g function as your input. So basically you're saying f of x plus 1. So you have 2 times, remember this is your input, so wherever you see x up here, you're going to substitute this in. So 2 times x plus 1 squared minus 1. So x plus 1 squared, remember, is x plus 1 times x plus 1. So x times x is x squared, x times 1 is 1x, 1 times x is 1x, and 1 times 1 is 1. So this part would be 2 times x squared plus 2x, because I've got to combine my like terms here, plus 1 minus 1. So this would be 2x squared, because we're distributing now. 2 times x squared is 2x squared, 2 times 2x is 4x, 2 times 1 is 2, and then if I subtract out this 1, it would be 2x squared plus 4x plus 1. So this is the formula. So instead of doing that whole thing where you have to substitute into the g function and then substitute that into the f function, so if you wanted to know like what f of g of 5 was, like we did down here, all you would have to do is take 5 and plug it into this formula right here, and what you would get out would be the same answer as here. Okay, so now if we do the same thing, if we use g of f of x, what that's saying is we take the f function and we plug it into the g function. So g of f is equal to, so we're basically doing g of 2x squared minus 1. That was a horrible exponent there. Minus 1. So wherever we see an x in the g function, we're going to replace it with this 2x squared minus 1. So 2x squared minus 1, and then we have this plus 1 over here that we have to add on. So the minus 1 and the plus 1 are going to cancel each other out. So g of f, the function for that would just be 2x squared. So you can also see that in addition to not being commutative, they also do not have the same function. All right, here is your assignment for this one. So there's one assignment right there, and then we also have the second assignment here. So those should both be up on the website. If you have any questions, let me know, and I will talk to you soon.